Hi everyone, welcome back. In this video, we will be talking about orbitals and energy levels. So, first we will be looking at Bohr's model. So in Bohr's model, we will have an atom, let's say hydrogen atom, which has one electron, and this electron is orbiting around the nucleus in fixed energy states. So hydrogen only has one energy level because it's in period 1. But if we look at something like sodium, which will have 3 electrons, which will occupy 2 energy levels. And these energy levels are fixed circular around the central nucleus. And the first energy level, which we'll call it n equal to 1, can hold 2 electrons. The second energy level can hold 8 electrons max. The third can hold 18 electrons maxed, and so on, so forth. But actually, in fact, this Bohr's model is not accurate considering the nature of atoms and atomic motions. So if we look at the quantum model of atoms, we will actually have a more accurate illustration of atomic structure. So in quantum model, we will see that electrons, instead of behaving like a particle, they behave like a wave. So electrons' energy sort of dispersed in the form of a wave. And electrons also occupy space in pairs, and they have opposite magnetic spin. So later, physicists discover that around the central atom, a central nucleus, electrons actually occupy certain orbitals, which are a certain space that is occupied by pairs of electrons. And we will have a 90% of chance of finding electrons in the volume of this orbital. So in the first energy level, we will have the s orbital. And the s orbital, we can interpret this as sphere to help you remember. So it's a spherical orbital which can hold 2 electrons. And it looks like if this is the nucleus at the center, the s orbital would be just like a sphere around the nucleus. And this orbital, just like any other orbitals, can hold 2 electrons. The next energy level or orbital will have p orbital, which we could interpret like peanut. So p orbital will appear starting from n equal to 2 all the way. So p orbital looks like this. So this is still the central nucleus, and p orbital looks like something like this. So we'll have 2 lobes around the nucleus, and this orbital will also contain 2 electrons, just like any other orbitals. And based on how we orient this orbital, p orbital, we will actually have 3 different configurations: x, y, z. We would have px orbital, which is two lobes on the x dimension, y orbital, which is on the y dimension, and finally we would have the z orbital, which is on the z-axis. So we would have px, py, and pz. And each of these p orbitals can hold 2 electrons each. So in total, we would have 6 electrons for p orbital. Starting from n equal to 3 all the way to n equal to infinity, we would have d orbital. And d orbital's shape is a little bit more difficult to draw. But understand that we would have 5 different configurations or shapes of the d orbital. And each of the configuration or suborbital can also hold 2 electrons each. And these 3 orbitals can help us to identify the electron configuration for the first 4 periods of elements more accurately. So for example, if I want to represent hydrogen, there are 2 ways to write it. First way, we can write the electron configuration of hydrogen using the orbitals. The second one is the orbital diagram. So we're going to look at each of them respectively. So first, let's look at the electron configuration. So if I have hydrogen which has 1 electron, which means we will only need the first energy level, n equal to 1, which will have the 1s orbital. This 1 shows which energy level this orbital is in, and this shows which orbital are we that we are referring to specifically. So we would have 1s orbital, and in this orbital we would have only 1 electron, even though it has a capacity to hold 2 electrons. While helium, on the other hand, has 2 electrons in total. But since the first energy level, n equal to 1, can contain 2 electrons, so we still only look at 1s. But this time, we would put 2 electrons into this 1s orbital. And the superscript denotes how many electrons are we have in this orbital. Let's look at a more complicated one. For example, neon. So neon has a atomic number of 10 on the periodic table. So the first energy level will not be enough to contain all the electrons. So we will have 1s, but now we will move on to 2s. And on the 1s orbital, we would have put 2 in it. 2s, we also put 2 electrons into this orbital. Now, since we're into the second energy level, we can have p orbital as well. So we would put 2p here. And remember, for 2p, we actually have px, 2px, 2py, and 2pz. And each of these suborbitals have 2 electrons in them that could be contained. So we can put 6 electrons in total into the 2p orbital. And 6 plus 2 plus 2, which is 10. So we have successfully put all these 10 electrons into the 3 orbitals. Now let's try orbital diagram. So orbital diagram uses arrows to denote electrons. And since they have opposite magnetic spin, we will use up arrow to denote the first electron that's being put into a certain orbital, and down arrow for the other one. So now, let's see how we can convert this electron configuration into the equivalent orbital diagram. So 1s, we would have one up arrow and one down arrow because we have 2 electrons in it. For 2s, we also have one up, one down. For 2p, we actually have 3 suborbitals. So we divide them into 3 little square boxes, and we will put the 6 electrons in. But pay attention to how I'm writing the arrows. I'm writing 3 upper arrows first and 3 down arrows next. And this rule is called Hund's rule. And Hund's rule says, in order to successfully fill in all the electrons for an orbital, we need to actually fill all the upper ones first and then down ones. And another principle that we're using consciously or subconsciously when we are filling into the orbitals is called Aufbau's principle. And this is German, which if we translate into English means building up. And this principle essentially says that when we're filling in the orbitals of a particular atom, we're always trying to start from the first energy level, second energy level, third energy level, and so on and so forth. So we don't skip, for instance, skip the first energy level and start directly from the second energy level, which is not allowed. And in fact, the whole sequence of orbitals for a particular atom with an atomic number Z is always 1s, 2s, 2p, 3s, 3p, like this for the first 5 orbitals. And each s orbitals can hold 2 if they want, and each p orbitals can hold 6 if they want. And next, since we are in this third energy level, we should have 3d next. But instead, we have a counterintuitive anomaly here. So if we look at this, we would have the nucleus here. We would have our 1s orbital here, 2s, 2p here, 3s, 3p here. And now, we should have our 3d here. Or this 3d should be fairly close to 3p. But since the energy levels are actually converging, the 3d and the 4s that we're going to have as the first orbital for energy level 4, they're so close that the 4s orbital actually happens before the 3d orbital. So we would actually have 4s before 3d. And then we would have the rest for fourth energy level orbitals. So for any atoms, we always start from left and try to fill in all the previous orbitals until we used up all of our electrons. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 4d. So that's all for this video, where we have discussed electron configuration, orbital diagrams, how Bohr's model is different from the quantum model for atoms and electron orientations. Thank you for watching.